Hi, in this video I'm going to talk about the panel data analysis. As part of this session, I'm going to cover the following topics. The panel data, what is panel data, and then talk about how to analyze panel data, and then I'll talk about the estimation techniques used in panel data analysis. I'll then talk about the LM test, Horstman test. You might have heard about time series data and cross-section data. So let me give examples of time series data and cross-section data. The time series data looks like this. You have got the stock price of a particular stock over a period of time, continuous period of time. So you have got stock price for 1st December, for 2nd December, 3rd December and 4th of December. So you have stock price data for 4 consecutive days. That's time series because it has data for different time periods, and the difference between the consecutive time period is constant because it is only 1 day difference data. What is cross section data? In cross section data you won't have the time component. So here is an example. We have got data for different cities in United States for a particular year. Let's say the year is 2014. So for 2014 we have got data for 3 cities, Florida, California and New York. We have got the population in millions, average income, percentage educated, and then the rainfall. Okay, so I've got data for different cities for a single time period. That's important, single time period. Okay, so in cross section data you will have data for different cross sections only for a one time period. Okay, whereas in time series you have only one kind of data. For instance, here we have the stock price but for different time periods. So that's the difference between time series and cross section data. Now what is panel data? Well, panel data is just some kind of a combination. The way if you combine time series aspect and the cross section aspect of data, then we get a panel data. So let's take an example to understand. So here is an example. So remember in the last slide we talked about a data set which has got information about different cities in United States. So we've got data for Florida, California and New York. So we've got data for population, average income, percentage educated, rainfall, and we have got another column here which is time. Remember in the previous slide we talked about the cross section data which has got data for only 2014, but here we have got the same data for 2015 as well. Now here we have data for 2 years. Okay, 2 years, or in general we have got data for multiple years, okay, or more than 1 year. So in that case we call this as a panel data because we have got cross section data for multiple years. Now this is our cross section data. So this is the data that we had in the previous slide. So this is the cross section and this gets repeated for 2015 as well, and you can extend to 2016. Panel data can be categorized into 2 types. One is balanced panel data and the other one is unbalanced panel data. If you look at the right hand side of the data set, so this one, so this is the one that we have taken from the previous slide. Okay, so this is called balanced panel. Why? Because we have got data for the 3 cross sections and then we have got data for exactly the 3 cross sections without missing out on any one of them. But what if we miss out on just at least one of them? In that becomes unbalanced panel data. If you look at the left hand side of the data, you see that we have got data for Florida, California, but the data for New York is missing. Whereas we have got the data for New York for 2015, but for 2014 the data for New York is missing. So this is called unbalanced, where you have different cross sections. It's not the same set of cross sections which are getting repeated for the next year. It is a different set of cross section which is there for the next year. So if any one of these is missing, which often happens in panel data analysis, where we could come across cases where we have got missing data that becomes unbalanced panel data. Panel data allows the control over variables we cannot observe or measure. Okay, and we'll understand this. So what is that we cannot observe? Okay, in great detail. Take the example from the previous slide. We have got population for a particular city, let's say Florida. Okay, so we have got 10 million, and then the next year the population for Florida is 12 million. So not only we are having the data for Florida for a particular year, we are having it for different years. So we know the trend that is there in this particular data. So we have two advantages of having panel data. We have got trend, okay, within the variable, okay, and we have also got variation across variables. Okay, so that is a combination of the features of panel, the features of cross section and time series, and that makes it interesting to analyze. And if you do an analysis for 20 years, let's say you're doing an analysis from 85 to 2015, so you're doing analysis for 30 years, a lot of things would have changed about the population. People aren't the same what they used to be 30 years ago. So there are certain aspects of the population that changes over time. Okay, so that can only be captured in a panel data analysis and not in a cross-section data analysis, and that's one of the important features of panel data. It also accounts for the individual heterogeneity. Okay, that means how within the individual things change. For instance, how the population is changing over time for Florida and how it is changing for New York. Okay, so one can compare how Florida is the certain certain feature of the state Florida is changing over time compared to New York. So the comparison is also possible in panel data. How do we analyze panel data? Okay, is it the same that we normally use for cross section? So important thing is that it has got both the features, time series and cross section. So the question here is, can we use the ordinary least square? Now there is going to be problems. A typical OLS model looks something like this. Yi is equal to the estimates a plus b xi plus error term, whereas a model form for panel data looks like this, yit. So the extra component or the extra thing here is the time component. So I stands for the cross section, T stands for the time series. Let's go both the components, right? For instance, in our example, I stands for here the cities, New York, Florida, and so on, and time stands for different time period, 2014, 2015, and so on. Okay. Now, in this particular case, you will see that the errors will most likely to be correlated for a particular cross section. If you take the population for Florida over time, over 2014, 2015, 2016, and even before that, you'll most likely find the population to be very correlated among themselves, right? Hence, the error term are also most likely to be correlated, and that is an issue in OLS. Okay, so either that has to be corrected before using OLS, or you can use alternative technique. We'll see how we can deal with this problem and how we can overcome this problem while doing panel data analysis. A simple case. So what we're trying to do here is we're trying to predict, we are trying to rather understand the relationship between the salaries of employees, different covariates for different independent variables. Okay, the independent variables are the experience of the employee, the projects, the number of projects that the employee has taken up in his career, and the education, number of years of education the employee has. Now these are the three covariates, and we have got the logarithm of salary as the dependent variable. So this is the dependent variable, and the independent variables are experience, projects, and education. Okay, so we will have a model like this, right? There will be three estimates, and we have the uh, experience, then projects, and then education. Okay, all right. So the model will look like this. Now, question is, why do we take a logarithm of salary instead of salary? Well, in some research, people take logarithm of certain variables so as to have a better model. And one of the reason they take is to reduce the variance. That's one of the reason, and there are other reasons as well. Okay, so we've taken the logarithm of salary as the dependent variable, and we've got three independent variables. So this data is available for different time periods. Okay, and we have got different employees. So for employee ID 1, we have got data for 7 years, right? If you listen number of years of education with salary. So what we're trying to know here is the marginal effect, like how experience impact the salary of someone. We're also trying to know the relationship in terms of the sign, whether it has a positive effect or negative effect, and so on. Pretty much similar to the multiple linear regression, just that the structure of the data is different in this case. Okay, one of the analysis is pooled OLS regression. It's one form of regression, OLS regression, that you can use instead of panel data. Okay, the reason why we are trying OLS regression is to show you the weakness of this technique. Okay, weakness. Also to show you that why this particular technique is not very suitable for this type of data set, right? And that will ensure that we have a strong argument for going in for a panel data analysis. Okay, so the only thing that is uniform in these two groups is the variance of the error. Okay, so the error variance is constant. That is what is assumed. So only thing you need to remember here is that the error variance is uniform across different cross section. Okay, so that is one assumption in pooled OLS regression, and we'll use this in this data. So how do we use this? We use the PLM, and then we have got the dependent and we have got the independent. So we have just coded this. So in independent you have the three independent variables, right? We saw in the data set. We have got the data, input data, the same data that I showed you, and in the model you have to put it in so we are using pooling in this case. So just provide pooling to this particular statement, saving this in a variable called pool. So this is the syntax. Okay, simple syntax, and if you're familiar with R, you should find it very easy. Okay, so we're just taking a procedure PLM, which takes argument, which has independent variables, dependent variable, the data, and the type of model that we are trying to a type of panel data models that we are trying to fit here. So we'll see some of the statistics in this particular result. So in the results we have got the intercept and the slope coefficients, the R square and the adjusted R square. Remember, this is OLS, so we'll of course get these these things in the results. So what we can see here is that two of the variables are significant. Right? Experience is significant because it's less than 0.05. Similarly, education is also significant. Number of projects is not a significant variable in determining the salary of an employee. 0.35, and the adjusted R square is also pretty much the same. So that's what the result from this particular model. Now, is it good? No, it is not good model because it's a bad fit to the data. Okay, we can actually have a better model. We can actually have a better model with higher R square. Okay, with higher R square, which signifies the model's strength. Okay, R square, the higher it is, the better it is, right? We want always very high R square. We want always it to go up. So it ignores the fact that it is a panel data. It's simply we are fitting a cross-section model to a panel data. So of course we will expect a not so good model, and that's exactly what we're getting here. We're getting only 35% of R square, which is not a very good fit to the data. And this is happening because the error terms are correlated and we are not taking care of that. Okay, so we are losing out a lot of information in this particular type of model. Okay, the next one that we're going to do is the between estimation. So this is the estimation type 2. Okay, the pooled one was 1 and this is 2, the second type. So what it does is it calculates the average of the dependent and the independent variable over time and does the OLS regression of the dependent by taking the independent variables. It's pretty simple. So what it does is we have got time series as well as cross extended, right? When we do the average, if you take the average over time, so you'll only get the cross section, right? What do? You simply take the average over time. You have got 7 period, right? 1 to 7th. So you take the average of education, the average of the number of projects, the average of the third variable as well. Okay, and if you do that, the time series component is gone now. Now you don't have data for all 7 years. You just have data for the average of the 7 years. So we are now have if you do that, we do not have to deal with time series. We just have to deal with the cross section, and that is also going to be an issue. But I'm just showing you an alternative technique, like what are the options that you want. Even if you use between estimation, it is not going to be optimal in nature. It might be a little better than the pooled OLS regression, but may not be the most optimal one. So the syntax remains same, except the fact that in the model statement we are using between instead of the pooled that we had used last time. Results are pretty much same, except the fact that the R square has gone up now. R square has 0.4 instead of 0.35 the last time we saw. Now, as I was initially, I was talking to you in the last slide that the R square might go up, but we are not sure if this model is the optimal fit. And it has certainly gone up, but it is definitely not the optimal one. It can go up even higher if we use a right model. Okay, so the between estimation is also not a fit to this data. One thing you need to remember here, probably you have to revisit the theory, and I strongly recommend you to learn the pooled estimation and the combined estimation. You should go through the theory to understand this particular this better, because I'm not able to cover like every single thing in this particular video, because the the main purpose of this video is to learn panel data, not the OLS one. So I'm just talking in brief about this estimation, but you can always go through the theory to get a better understanding. So in combined estimation, all we are doing is we just averaging it out over time. Okay, so we have got education. Let's, for example, we have got education, number of education for education of course will not change. Let's take one data. Okay, let's say experience, right? So experience is changing over time. So this is the experience for the first individual, right? We're just taking the average of that in between estimation. Similarly, the number of projects, we're also taking the average of that. Okay, so when you take the average of that, all these 7 observations, you'll only get a 1 value, right? So the data will be will not have any time series component, and that's exactly what happens in between estimation. In pool estimation, we don't do that. We still have all the 7 observations, but in between we only have the average of the 7. That's why we have got rid of the time series components. What is the next one? The next one is the first difference estimation. In this particular type of estimation, we exploit some feature of the panel data. Okay, so what we do is that we take the first difference of the two equations, for different time periods. In time series, we've got the lags, right? So if xt is known as the data for the current time, xt minus 1 is known as the data for the lag period. Similarly, xt minus 2 is the data for the next lag period, right? So this is how we represent a time series data. If you're familiar with time series, this is pretty easy for you. If you're not, so this is how we represent the time series data. So we've got two types of equations here, two equations rather, yit and yit minus 1. So this is for the lag period. Okay, similarly for the independent variables, we have got xit and xit minus 1. Ci is an individual effect. Okay, individual effect as in the effect that is purely for different individuals. Okay, in this example, we have got the data for the employees, right? We have got data for the employee. Apart from the three variables, there are other things about a particular employee that also matters, right? For instance, the IQ level, right? So if you compare two employees with same education, same years of experience, same number of project, you still find a difference in the salary. That could be because of the IQ level of two employees. Okay, so the university or the school that a person attended, that also could matter, right? University also could matter. Then family background, parents' income, right? That also could matter for the salary of an employee, right? Somebody who has gone to a better school or a better university, whose parents have been able to spend more money or more time for for a particular employee, then there is a higher likelihood. The likelihood that he would have been able to more successful in his profession would have been higher, right? So given these three variables same, you will still find the difference in the salary for two persons, and these are individual specific things. Okay, individual specific things, or also we call it as the unobserved variables or unobserved features of the data. Remember in the first slide for final data, we talked about the unobserved things, and I had told that time that I'll be talking about in detail. So this is exactly what it is. Now we capture that in a variable called Ci. I stands for the cross section because that doesn't change over time. Also, that's an assumption here. So we just see that the unobserved thing is very specific for a particular employee. So it could be C1, C2, and C3 for employee number 1, employee number 2, and employee number 3. And they will, of course, differ among them. Okay, so that component is captured in Ci. When you take first difference, what is first difference? You just simply subtract the lag from the original variable. So, okay, so if we take yt minus 1, we essentially call it as first difference. Okay, and then we take yt and you can go on, you can take second difference, third difference, and so on, but this is first difference, and we do the regression by taking the first difference, and that's why it is called first difference estimation. So essentially what we are doing here is that so we are taking the first difference here. So in the left hand side, we'll of course have something like this, plus you have got beta 1 x1 it, then beta 2 x it minus 1 plus ci minus ci. Remember, the unobserved factor gets cancelled out in this case, and then you have the error term and so on. Now that's interesting. When you take the first difference, you actually get rid of the unobserved impact or the individual specific effect on the dependent variable, and technically we call that as individual heterogeneity. Okay, which essentially means the variation or the effect of unobserved things on dependent variables. We technically call it as individual heterogeneity is eliminated from the model by taking the first difference. Particular type of regression by taking the first difference, by getting rid of the individual effect. Syntax remains same except the fact that in the statement model you're just using FD. So what are we getting here? We're just getting one significant variable, okay, and that is projects. Okay, so education and number of years of experience hasn't been significant. Now that's a little strange. Okay, so what about the R square? The R square is extremely low. Okay, now we are getting two strange events. One, that two important variables, education and number of years of experience, are coming out to be insignificant. So that's strange, because you wouldn't expect these variables to be insignificant in such cases. Why? Because these are very important in determining salary. So that's common sense, right? And R square is also pretty less, 0.007. That's like less than 1%. So that's totally strange, and this result is unacceptable. So you've seen education got dropped because education doesn't change over time, right? So it's totally got dropped, right? Number of year experience is coming out to be insignificant. So this model is also not so very good. Okay, in fact not at all good. This is totally giving a very weird results. The next type of model that we'll talk about, and this is the pure panel data model, so to say. Okay, one is the fixed effect model, or we call it as fixed effect panel data model. Okay, popular ones, fixed effect panel data model. So what it does is it treats the unobserved individual heterogeneity. We talked about unobserved individual heterogeneity in the last slide, right? And when denoting is alpha I, so we had denoted as Ci. Let's not confuse with the notations. Same, right? We're just changing notations. Okay, so it's alpha I in this case. So we'll not confuse with the alpha I, which is the intercept here, right? So let's not confuse with that. We'll keep on using alpha I for the individual heterogeneity. So we assume here is that the unobserved heterogeneity for each employee to be correlated with the explanatory variable or the independent variables. Okay, so that's an assumption. So we say that alpha I is very correlated with xi or xit. Okay, so the correlation between alpha I, which is the individual heterogeneity, is with the independent variables is non-zero. Now this is an assumption. Okay, if this happens, we'll be using fixed effect model. Now the obvious questions is like, how do we know this is there, right? We'll see. How do we know that this is 0 or non-zero, and what if it is 0? Okay, we'll transformation to remove the unobserved effect, pretty much like the the first difference estimation type. Here also we are going to get rid of the alpha I term, the unobserved effect, before doing the estimation. So fixed effect transformation will look something like this. The original model is YIT, and then we have got the unobserved effect. Let's ignore the intercept for the moment, and then we have got the slope coefficient beta, and then we have got independent variables and the error term. When we average it, right, average it over time, we'll get rid of time component, right? I have told you previously also, if you have data for time t1, t2, t3 up to t7, you average it, you get only one value, right? And that doesn't have time, right? So yt minus 1, yt minus 2, it could be 1 to minus 7, because they've got 7 data points for 7 time periods. If you average, take the average, you will have only one data, right? Y bar, which denotes the average, and it doesn't have t component, it only has the cross section component I. So we have averaged it out over time. Now we subtract. Okay, now we subtract these two equations. So the first equation and the second one, which is the average of the first equation. Okay, remember the difference. The difference is that here we have only cross section because it's averaged over time. So I've got rid of the time component, and here it has pure panel data. Okay, so when you take the difference of that, you will get certain kind of equation which is used for fixed effect estimation. Okay. The interesting thing is that, when you take the difference, the unobserved effect alpha I will get cancelled, right? When you take the difference, it is going to be 0. Alpha I minus alpha I is 0, of course. So that is totally out of the equations. Now the estimation will be possible. So we're getting rid of by eliminating the alpha I in this case. And the LH side is known as the time demean Y. Okay, so these are technical terms that you need to remember. Time demean is nothing but getting rid of time. So technically we call it as time demeaned. Similarly, we're also getting rid of time demean, or we are having time demean X values, independent variables, as well as the error term. Now let's apply this concept to our case study, right? That one that we have taken. Now on the time demeaned data, we can actually use the OLS regression. Okay, why? Because when you have time demeaned data, your errors will not be correlated over time, because you have only cross section error I, J, K, and so on. So you don't have error like UIT, JT, and then UIT minus 1, UJT minus 1. So we expect these to be correlated because there is a time component over time, right? Like the salary of the same person over time. Okay, salary of the person 1. Okay, person 1 for time 1, and salary of the same person in time 2 will most likely to be correlated. Now since we have got rid of the time component, that thing is not going to be there. So errors are not going to be correlated over in this particular case. So we can use OLS now. So by doing this transformation and using OLS, we are estimating the equations. So this is all theory. Syntax remains same that we have been using so far. The model type is now within. Now the fixed effect is also known as within effect. Okay, so fixed effect is same as within effect. Okay, so let's not get confused in this case. Let's look at the results. Now in the results we can see that there are two important variables which are significant. One is experience, the other one is projects. As expected, right? These two are very important variables for somebody's salary, right? So they're coming out to be significant. What about the R square? Now the R square is 0.65. Adjusted R square is 0.56. Now that is significantly higher than the R squares that we have seen in the previous 3 models, right? Why it is so? Because now we are using the correct methodology, right? So if you use the right estimation technique, the right model for the data, will have a better R square, a better fit rather. Okay, so this is better fit to the data. Previously we were using wrong models for panel data. So we weren't using panel data model. So this is the panel data model, and that's why we have got the better result. The reason, I mean, when you are doing in practice, you need not have to try, all 3 types of estimation that I showed you in the beginning. The reason I showed you is to give a comparison study, as to how OLS is different from the panel data analysis, and how we can actually empirically show that the panel data models are better fit to the panel data than the OLS models. So how do we interpret? Now education is dropped. That is fine, because education doesn't change over time. When we have taken the average, of course it is not going to be there, because education doesn't change over time for a particular person, most likely. So it gets dropped. Experience has a positive effect on log salary. Square value is pretty good, so that shows that it's a good model. The next one and the last estimation technique that we'll be using, which is always compared with the fixed effect model, is the random effect estimation. And in panel data analysis, you will always be trying either fixed data estimation, fixed effect estimation, or random effect estimation. Now, the fundamental difference between the fixed effect estimation and random effect estimation is that it assumes that the individual specific effects, the unobserved effects, I'm talking about the alpha i's, are independent of the regressor. Okay, or the correlation between alpha I and xi is zero. In fixed effect, we had non-zero value. In random effect, it is zero. So that's the fundamental difference between a random effect estimation and the fixed effect estimation. That, and there will be several questions related to when to use random effect and when to use fixed effect, and it's an important one. And in the last part of this presentation, I'll talk about how to decide which one is better, right? Fundamentally, we know the assumptions are different, but how do we know that there exists correlation between, the alpha I and xi? Do we have to do it first before, deciding on which one is to be used? We'll see that. So let's use this first. We use the, the statement model equal to random in this case. The rest of the syntax remains same. And where we're getting here is that experience is significant, education is also significant, but the R square value is going down. Yeah, it's 42% now. So previously we used to have 65%, it has gone down. But just by looking at the R square, we cannot say that which one is the best model, because best model for this particular data, we have to verify it statistically. So now we have come down to two models. One is fixed effect model and the one is random effect model, and we'll see which one is most suitable for our data, which one fits our data the best. Okay, for that we'll do the LM test. Is used to decide whether you should, your data fits random effects versus the OLS. Okay, you might wonder that we are confused about random effect and fixed effect, where we testing with respect to OLS. We'll see that. Okay, so let's just bear with a few more slides. We'll have everything in place. So listen to me just few more minutes and everything will be clear. So the LM is used to decide between random effect regression and a simple ordinary least square regression. Okay, and we'll be using the PLM test function in order to do that. The null hypothesis is that there is no significant difference across the cross-section unit. Okay, so that's the null hypothesis, which implies that the random effect model is inappropriate. So if we are in favor of null hypothesis, then random effect is inappropriate. If we're not in favor of null hypothesis, we're in favor of alternative hypothesis, then we will see that random effect is appropriate. Okay, when we do this, so pool is the result that we have used previously, right? So we just use that, and we're using the function PLM test. So what we're getting here is that the p value is significant. What does that mean? So that means that the null hypothesis is not in favor of the OLS. What we can infer from this is that given the fact that the p value is less than 0.05, that means it gives us some kind of a significance. So null hypothesis, the importance of null hypothesis, gives us the confidence that random effect model is better against OLS. Okay, so we'll go ahead with random effect model instead of OLS. Okay, so just look at the p value. If it is if it's less than 0.05, then go for random effects. That's the rule of thumb